In this series, I'm going to be going over the MIT OpenCourseWare course on electricity and magnetism. For reference, I'm a high school student and this is college physics, so we'll see how this goes. I want to create a unique dynamic where I'm both the student and the teacher. This is episode 2. So, in the last episode, we talked about Coulomb's law. And if you haven't watched that episode, I highly recommend you do because it's just important to have all that background knowledge. So, let's just review what Coulomb's law is. Coulomb's law lets us find the force between two charges, and it does that by using Coulomb's constant, which again is just a number, charge 1 and charge 2, which is just the charges of the two objects. You multiply them together, and then that's just divided by the distance squared, which is the distance between them. Now here's a question for you. What if we want a mathematical representation for just a single charge? Coulomb's law uses two different charges. What if we wanted to just use one charge? And we know that if we have one charge, it's going to interact with charges all around it. And the interaction is only based on the other charge, but we know a lot of things just by knowing that the properties of the one object that we have. So how would we do this? So let's go back to Coulomb's law. Let's think about this. The first thing I was thinking of, and which is ultimately what we're going to do, is just dividing by one of these charges. So just think about it as just getting rid of one of these charges. So we're just left with Coulomb's constant, one of the charges, and then all that is divided by the distance squared. And of course, no longer will we get force because we're removing one of the properties, but we'd get force divided by that second charge, which is, what we're doing because we're dividing by both sides. So what exactly is this? And we have a name for it, and it's called the electrical field, and it's essentially what I just talked about. So you have the electric field equals Coulomb's constant multiplied by k over r squared. And r and d are the same, it's just radius or distance, but you can think of them as the exact same because they are. So what does this do? Like, if we think about this before looking at any graphics or anything to make it easier, just by this formula, we can actually understand a lot of things about what the electric field actually is. We know that the constant is always just going to be a constant, so we can almost always just not care about that. Then we have the charge. So it's basically telling us that we can plug in any radius and we can get out a number. And this number has something to do with the force around that object. And we can do this for every single point around the object and get a number value, right? So that's just something to keep in the back burner until we look at some graphics to make this idea a little bit more simple. So using this equation, we get this new force equation, right? And the way it's laid out right now, it might be a little difficult to understand, but when we looked at Coulomb's law earlier, we had F, and then I said we were dividing both sides by this Q, and then we were left with the electrical charge. So another way to think about this is the force is equal to the electrical field. Sorry, I said electrical charge. I meant electrical field multiplied by the charge that we're looking at. Now, just a reminder, with all these Q's, you have to make sure you know which Q you're talking about. Inside the electric field itself, we have a Q, and that represents the single point charge that we're talking about. This Q represents a different external point that we're trying to understand how they interact and then find the force between them. So this is, I think, will be very important in the future and important to just know in general. So now let's look at a graphical representation. And so far, everything might seem a little bit hard to understand, and it was definitely for me, but once you look at some graphics, it makes more sense. So this is what we call a vector field, and it's just a field of vectors. It's just, it's not too complex of a topic, but it's kind of that idea I was talking about earlier. For each point in space, we assign a magnitude and a direction. So For example, in this scenario, we would have a charge right here. And we can kind of see this field that forms around it because of that electric field equation. We've solved for every point, and we've kind of put the size of the arrow indicating the value, and there's also a direction that will always be parallel to the radius, right? So another thing to note is the direction. You might be thinking, well, is this like a positive charge or is it a negative charge? And the convention that we use is that we're always looking at the way that the arrows are pointing is going to be in the direction that a positive charge would go with. So if there was a positive charge over here, they'd kind of go with the flow over this way. And if there's a positive charge over here, they'd go this way. Now, what does that tell you about the charge that's here? Well, then it would also have to be positive, because last episode we learned that like charges repel each other. So this is an example for the electric field around a positive charge. Now let's just look at an example of two different charges together. Now before we begin, based on just the explanation I gave in the last one, where are the 2 points? Which one is positive and which one is negative? So hopefully you've taken a second to figure that out. And this one is the positive charge because all of the arrows around it are going away. So if we take a positive charge and put here, it kind of follow this path up here, and it would kind of curve over here. And if this one's positive, then this charge must be negative because all the arrows are pointing inward. So we kind of see if we put a positive charge right here, obviously it's going to want to go away from this positive charge. So it's going to flow this way and be attracted to this negative charge. And we see just really any point, you can tell why it's going that way. So if you look at here, it still has repulsion from the positive charge, but then it's starting to get attracted by the negative charge, so it kind of circles back and then ends up to the negative charge. Now let's talk about field lines. And now field lines are, you can imagine the same vector fields as before, but we're just drawing lines over the path. So this is actually the exact same example as we had before. The other one just kind of went more above and below, but this is really all we need. So again, if you have a positive charge, you can kind of just follow with the lines, and you'll be able to trace out the forces that affect this this positive charge. Now note that I didn't say trajectory, and that's something a lot of people might get confused about. If you have a positive charge right here, it is not going to follow this line to a T, right? This is not modeling a trajectory. It's just the electric field that is modeling. So if you have a positive charge right here, it's going to have a force tangential to this line. So it's going to have a force kind of going in this direction. So instantly we see that it kind of goes off the line, and it kind of goes in this arc that we have. So it's not going to follow the line, but eventually it's still probably going to end up over here. And at each point you can figure out the force, but not the trajectory. Now, in the last episode, I talked about the similarities between Coulomb's law and Newton's law, universal law of gravitation. So the same thing is kind of true with the electric field and the gravitational field. Now we can think of masses as having a field around them. And we know that this is just a force of attraction, right? Everything kind of goes in towards that mass. So if you're thinking about this as a charge, in a sense, you could think about this as a negative charge, because everything is attracted, all the positive charges are attracted to it. Obviously, gravity and electricity are two different topics, but just another parallel that we can make. Now, the next thing I want to talk about is a dipole in an electric field. So what is a dipole, right? A dipole is actually a very a simple concept, and I've actually showed multiple examples today, and this is just one of them. So a dipole is essentially a positive and an electric charge, negative charge that have the same electrical charge, right? So the magnitude of their charge, if you're solving for Q, it would be the exact same here. And it kind of creates this pattern as you see, and as we explained before. So that's what a dipole is. And now what's interesting is when we put that into an electric field, right? So we have this electric field here that's going from the positive to the negative. We see that the positive wants to repel against this positive, right? It wants to go with the lines. So again, this force is going to be tangential to the electric field, right? So we see that these are two parallel lines here. So there's a force going this way. But obviously the negative wants to go this way because it wants to repel against this side negative and go towards this side positive. So it's going to go against the lines. And that, again, is also going to be tangential. And now what happens is, because you have these two equal charges, right? It's very important that they're equal. Neither side can necessarily win and getting to their goal. So they kind of just stay fixed here and they kind of just rotate, right? And they're going to rotate this way, and then they're going to kind of overshoot it, right? And eventually they'll keep oscillating here until they become parallel with the field lines, right? So the best case scenario for each of these particles is that the positive would end up right here and the negative would end up right here, right? They want to be at the end, but the other side is stopping them from doing that, so they kind of compromise in the middle. So they're going to do this oscillation pattern until they kind of get into that middle. So that was really it for electrical fields. I hope that wasn't too complicated. Make sure that you watch the last video on episode 1 about just electric charges in general. That's very important. In the comments down below, please tell me what I can improve on. Always looking to improve. And stay tuned for the next episode. Thank you.